Hello, my name is Alexei. Let me introduce you to my research related to electrochemical fabrication of bismuth, telluride, bismuth superlattices for thermoelectric applications. Bismuth telluride is one of the best thermoelectric materials at room temperature, but the thermoelectric figure of merit, even of bismuth telluride, is insufficiently high for most thermoelectric applications on a large scale. The prospective way to improve significantly the figure of merit of the interlaid structure of bismuth telluride consists in breaking the trade-off between thermal and electrical conductivities of individual bismuth telluride by introducing interlayers between bismuth 2 tellurium-3 quintuples. In this work, we have developed the electrochemical synthesis of simplest superlattice structure based on bismuth telluride and bismuth 2 tellurium-3 bismuth superlattice with bismuth atomic bilayers. These superlattices are of interest as thermoelectric material in itself and can be also used as initial substance for preparation of more complex superlattice thermoelectric structures. Our electrochemical procedures and experimental evidence of the superlattice structures have been published lately in Journal of Power Sources. So the main goal of the presentation is a brief overview of the electrodeposition and the latest results of its optimization for fabrication of the superlattices in the form of compact high-quality films. I will also present our results on the further electrochemical modification of the electrochemically deposited superlattices. According to the phase diagram of bismuth tellurium binary system, heterogeneous system is formed at high tellurium content, whereas high bismuth content favors formation of variety of stoichiometric compounds like bismuth 2 tellurium-3, bismuth 4 tellurium-3, bismuth 2 tellurium, etc. A 5-atomic layer, bismuth 2 tellurium-3 quintuple, can be combined with 2-atomic layer of bismuth, bismuth bilayer. In literature, structures formed by combining these two types of building blocks are designated as infinitely adaptive structures. The infinitely adaptive series is not limited to stoichiometric compounds. In fact, any composition between these two lines on the phase diagram is possible. This slide shows cyclic voltammograms for the electrodeposition of bismuth telluride from the solutions of its precursors and the subsequent anodic oxidation of the electrodeposits. The film deposition is a reduction process and it proceeds at negative potential. Bismuth 2 tellurium-3 oxidation proceeds at more positive potentials. With increase in concentration of bismuth cations in the electrolyte used for the electrodeposition, an additional process is observed in the anodic scan. The potential corresponding to this process is intermediate between the oxidation of bulk bismuth 2 tellurium-3 and metallic bismuth. This process corresponds to selective anodic oxidation of the interlaid bismuth in bismuth 2 tellurium-3 bismuth superlattices, and the thorough proof of this was presented in our article in Journal of Power Sources. For the electrodeposition of the films of bismuth 2 tellurium-3 and superlattice structures, we chose the pulsed electrodeposition mode with a square potential waveform. Deposition potentials were determined from cyclic voltammograms. Here are the potential and current profiles in the pulsed electrodeposition of the superlattice. The cathodic current is attributed to the film deposition. Anodic current prevents nucleation of bulk bismuth and controls bismuth interlayers. The composition of films determined with atomic absorption spectroscopy shows clear dependence on the electrolyte composition, and this provides efficient control of the relative number of the building blocks in the superlattices. X-ray diffraction patterns correspond to high degree of crystallinity of the synthesized bismuth tellurium films and show no peaks related to other phases. The position of peaks is slightly variable. We applied profile fitting to determine the corresponding variability of the lattice constant and what we expected to find out from the refinement. In literature, the compounds of this series are described with the so-called stacking model. The stacking model assumes no interaction between stacking blocks. Lattice constant, according to stacking model, can be calculated using the following formulas. On the other hand, structure optimization with density functional theory calculations has disclosed the interaction between stacking blocks, manifested especially in the shrinking of C lattice parameter. Our experimental results fall in between those predicted by density functional theory and the stacking model, thus indicating the interaction between the building blocks of the superlattice. The refined lattice parameters were in the agreement with the microscopy data as shown in this slide. One more evidence of bismuth bilayers formation was found from analysis of binding energies corresponding to 5D bismuth core levels in X-ray photoelectron spectroscopy. As we electrochemically obtained the superlattices deliberately in the potential region of metallic bismuth anodic oxidation, though below the potential of oxidation of bismuth interlayers, the observed contribution of bismuth in zero valence state in X-ray photoelectron spectroscopy spectrum was a convenient indicator of the interlayers. Returning to cyclic voltammetry, what we see is that the anodic oxidation of bismuth bilayers proceeds well below the potential of bismuth 2 telluride-3 anodic oxidation. And this gave us the idea to selectively oxidize those bismuth bilayers, leaving the crystal structure distorted. We compared the effect of the anodic treatment at the potential of bismuth bilayer anodic oxidation and different bismuth content in the electrodeposited films. The composition of films almost corresponds to bismuth 2 telluride-3 after oxidation, while lattice parameters were not affected by the oxidative treatment, except the case of very high initial bismuth content. The morphology of the electrodeposits was controlled by parameters of the pulsed electrodeposition. First, the duty cycle, which is the ratio of the cathodic and anodic steps duration in the potential control waveform. The particle size generally increases with duty cycle, which results in rough, non-uniform films and too high duty cycle. As for the pulse frequency, the excessively high pulse frequency lead to the formation of large crystallites and dendrites, but alteration of the deposition and refinement potential at moderate frequency was required to exclude the product of contamination by metallic bismuth. In order to facilitate nucleation on bare substrate, the electrode has to be prepolarized at the potential more negative than that used for the film deposition. We used pretreatment at -400 millivolts for 30 seconds to provide uniform coverage of the stainless steel substrate surface by the electrodeposit. The excessive pretreatment led to formation of large crystallites. To avoid non-uniform electrodeposition, also the solution has to be stirred and the surface active substance has to be added 60 minutes after the beginning of the electrodeposition. The time of the addition is important as surface active substance prevents nucleation of bismuth telluride if added at too early stage. So, concluding my presentation. We developed the electrochemical way of synthesis of layered superlattice structures with controllable composition composed of bismuth 2 telluride-3 layers and bismuth bilayer building blocks, verified their structure by X-ray diffraction, X-ray photoelectron spectroscopy, and high-resolution electron microscopy, and optimized the deposition process to produce films with good morphology required for thermoelectric applications. Additionally, we found out that selective anodic oxidation of bismuth bilayers and removal from the superlattices is possible and results in expanded bismuth 2 telluride-3 structure, which is of interest for introduction of other elements. This research has received funding from Horizon 2020 Research and Innovation Program, and thank you for your attention.